Okay, we're going to take a look at this proof here, and big idea is that we are trying to prove that the segment lengths AB and BC are congruent. We call those tangent segments. Tangent line would keep going. And picture B could move in, and then both of those would be shorter. So to any point outside of my circle, the two tangent segments are congruent, or the length from that point to the points of tangency. There are always 2 points of tangency, would be congruent. So that's essentially the what did we prove, or what am I trying to prove here. So given information, obviously our given information is that we have circle E. That means we know E is the exact center with tangents AB and BC. Stated just because sometimes it's hard for us to know exactly if there's more than one point of intersection here that are just really close and we can't see with our eye. And then step 2, we're being asked to draw in 2 things. So we're being asked to draw in actually 3 things. Segment AE and segment CE radii. So I've got 2 radii in, and then segment BE. I'm going to put that kind of as a dotted line through the middle. So I know there's a lot going through your head already because you're thinking triangles, right? There it is, triangles. And hopefully you're thinking, maybe we could prove triangles congruent. If we can prove triangles congruent, we have that lovely CPCTC that would say, okay, well, and this is just my thought, if AB and BC are congruent parts of congruent triangles, then if I know the triangles are congruent, then I would know that they're congruent. So I'm jumping ahead of myself, but just kind of putting together a plan. So following through step 2, what we did there is we used a postulate that says through any 2 points there is a line. We've referred to those as auxiliary lines, extra lines that we can draw in to help us, but the point is that if we have any 2 points, then we know there is exactly one line through them. Sorry about that. Okay, so from here, let's see what we know. Well, we know that AE and CE are both radii, and we haven't necessarily formalized this as a theorem, but let's just call that part of my, I guess, definition of radius or property of circles, that those are congruent to each other. And I'm just going to write out the statement AE and CE are congruent. All radii, plural for radius, are congruent in a circle. And then the second thing I know is that this segment that I drew in here, BE, is congruent to itself. So those 2 triangles share that segment. Okay, so I'm getting pretty close to having triangles congruent. So far I have a side and I've got another side, and I could either try to prove the third ones are congruent. Nope, that's what I'm trying to prove here. So I'm going to have to go for an angle. And if you think back to, there's a relationship between the radius and the tangent that I mentioned, but I don't know if we caught onto it. There's a relationship there. It might help to think of this extended as a diameter. That is an inscribed angle right there, angle EAB, formed by the radius and the tangent. And if we think of it as, again, the diameter, inscribed angle is half the arc. That's a semicircle, so therefore that's going to be a 90-degree angle. So I'm going to end up with a 90-degree angle, right angle there and here. So angle A is a right angle. I think I'm actually going to have to squeeze 2 steps in here, so I'm going to make this 5A and 5B, or you can obviously just add a step. Angle A is a right angle, angle C is right also. And so 5A is going to be tangent perpendicular to a radius. The other thing that you could say is that is a theorem that we didn't put a number with. You could also say that the angle is half the arc and say the measure of the angle is 90 degrees and then use substitution. So I'm going to say those angles are congruent to each other. Actually, no, I'm not, because the next step is I'm going to say the triangles are congruent. So I want to say triangle ABE is congruent to triangle CBE, and that's by HL postulate, which gets me to my CPCTC, corresponding parts in congruent triangles. So now I've got my, let's use this. Those two are corresponding parts of my two triangles, and that's what I'm trying to say are congruent right here. One quick fix is with HL, I actually don't say the angles are congruent. Do you remember what I have to say? Yeah, I have to say the triangles are right triangles. So I actually need to use this to say, if I was using any other shortcut, I would have used right angle theorem to say the angles are congruent. I want to say triangle ABE and triangle CBE are right triangles. And my reason is definition of right triangle. I just stated that they both have a right angle, therefore they must be right triangles. Okay, sorry for the sloppiness there. Hopefully that helps you understand what we just did. Everything good goes back to triangles, right? Even circles.